Hey everyone, how goes it? Welcome back to Computer Science 552 Game Development. Today, we're taking it to the next dimension by discussing 3D. Within our game production process, we are focusing primarily on game development. Within that process, now we examine concepts that are both important to programmers and artists alike. Today, we take it to the next dimension by discussing the graphics pipeline in relation to 3D. The graphics pipeline is a model that describes the queue of steps required for a system to draw a 3D scene to a 2D screen. More specifically, the act of drawing a 3D scene to a 2D screen is called rendering. The process can be broken into three sequential steps: application, geometry, and rasterization. The application step is the software executed by the CPU. Changes made to the 3D scene occur here. So for instance, input from the user, collision detection and response, and animation. The updated vertices and faces, typically triangles, move to the next step. The geometry step is responsible for generating the 3D scene from the information provided by the application. This establishes a world or global coordinate system and transforms all 3D objects to fit within it. Concepts related to transformations have been mentioned before and becomes a central feature in 3D. All major vertex and triangle operations occurs here. Looking into the geometry step a little closer, we see that it can be further broken into 5 steps: mesh and camera transformations, lighting, projection transformations, clipping, and window viewport transforms. Each substep handles a different aspect of 3D rendering. These will be detailed in several lectures. The rasterization step draws the 3D scene onto the 2D screen. Fragments or grid points correspond to 1 pixel in the frame buffer, which is 1 pixel on the screen. This is also where double buffering occurs. In relation to this, a shader is a program used to affect the rendering of a 3D scene. The types of shaders include 2D and 3D shaders. 3D shaders are used for a few different purposes. One is it calculates the brightness and the colors of a texture on a mesh's surface. Another is it can be used to modify the vertices of a 3D mesh. Shaders do a lot of work and mostly focus on how the 3D geometries are displayed. 2D shaders are used to affect the pixels after rendering a 3D scene. These can be used to create post-processing effects such as motion blurs, fades, and bloom. Shaders occur at different stages of the graphics pipeline. 3D shaders occur during the geometry step. 2D shaders occur during the rasterization step. Before we get into the finer details, let's start with the very basics: vertices, triangles, and faces. A vertex is a data structure that represents some attribute, like position or color. A position vertex is a single point in 3-dimensional space. For sake of argument, when we refer to a vertex, we are specifically referring to a position vertex. These are representation by data structures such as 3 components, x, y, and z, that correspond to the 3 axes in 3D space. Quick nifty tip: always know which direction is up. We may notice that it can change from program to program. Commonly, 3D vectors are used to represent vertices. These are just 3-component data structures that have been previously mentioned. An edge is a line segment created between 2 vertices. They are represented by an order set of vertices Vm, Vn. An edge vector between 2 vertices can be created by subtracting them. For instance, if we wanted an edge from M to N, this would be the vertex V sub N minus V sub M, as we can see here. A triangle is a polygon with 3 edges, where each edge shares exactly 1 vertex with another edge and creates a cycle. This is represented by either a set of 3 edges or an ordered set of 3 vertices. The ordered set of 3 vertices is more commonly used. This assumes that the edges created are created as a cycle. So for example, vertex M, N, and O would correspond to edge M to N, N to O, O to M. A face is a closed polygon created by vertices and edges. Generally, we can either pick triangles or quadrilaterals or quads. Triangles are generally preferred, and this is because triangles only have exactly one surface normal. A normal is a vector that is perpendicular to the face of the surface. As mentioned, triangles only have one normal, where a quad could have as much as two. Quads may have their vertices ordered in such a way that it creates two normal vectors, but triangles' vertices, no matter how you order them, only creates a single surface normal. To calculate the normal vector, if we assume that we have edge M, which is n to m, and edge n, which is O to n, then the cross product of edge M to edge n can be achieved by taking the determinant of the two column vectors em and en, as we can see here. The reason why normal vectors are so important is because a face's direction is based on its normal. Only faces whose normals point toward a virtual camera lens are displayed. Any faces whose normal faces away from the camera is invisible. One very important detail to note is that the order of vertices and edges matter. This is because the cross product is not commutative. A cross B is not equal to B cross A. In fact, it's anti-commutative, where A cross B is equal to negative B cross A. As mentioned, triangles have exactly one surface normal, which is why they're generally preferred. A mesh is a collection of faces that create a 3D object. In other words, it is called a polygon mesh. A surface is either all or a smaller part of a 3D object. 3D software is used to create 3D meshes quickly and save them to a file. And commonly their file formats are OBJ and FBX. Looking at one of these formats, we can start putting it all together. The OBJ file format is an open plain text format which contains the data for a 3D mesh. The type of data in the file is denoted by special characters. The pound or hashtag indicates that the line is a comment. V denotes that this is a vertex followed by an XYZ coordinate. VN means that this is a vertex normal and the vector components in an XYZ format. VT corresponds to the texture coordinates either in UV or UVW formats. This is going to be discussed a little later. F contains all the data related to a single face of the geometry and is formatted as the vertex index, texture index, normal index. For triangles, there are 3 per line. The vertex index is the order for which each vertex appears in the file, and it starts counting from 1. Triangles created by vertices in this format are assumed to be in counterclockwise order. When loading a 3D mesh, we must place the vertex information into a vertex buffer and the face information into an index buffer. The vertex buffer is generally an array that holds all the vertex data. The index buffer is also an array that stores the references to the indices in the vertex buffer. By using an index buffer, we can share common vertices and reduce the amount of memory required. Looking at this example, we can see the mesh to the left and the file to the right. If we start numbering our vertices from 1, then the highlighted vertex corresponds to vertex 5. This vertex is at the coordinate -1, 1, -1. We can see this referenced by the index buffer as being the first point on this triangle. Then we see the other points on the triangle highlighted in the index buffer correspond to the vertices 3 and 1, which are at 1, 1, 1 and 1, 1, -1 respectively. When we order them counterclockwise, we get this triangle. By doing this ordering, we know the normal vector points up and is visible to the camera. Now, let's take a look at an example. Before you is a 3D editing program called Blender. This program is very feature-rich and provides many tools to create 3D meshes, create 3D animations, and a whole lot more. This can be a daunting program to start using, so let's start with the very basics. First, let's look at the layout. What you see as the main window is called the viewport. Much like a game engine's editor, this is where we view our 3D meshes and we start creating them. Over to the side is the scene collection, which holds the reference to all the 3D objects in our scene. Commonly, we start with a cube, camera, and a light. Below that panel is the Properties Editor, which contains tabs for the object properties, its location, rotation, and scale, modifiers, which are extra modifications to be applied to the mesh, and we'll discuss that later on, and materials, which will also be discussed later on. Over to the side, we can see this drop down that refers to different modes. As mentioned, Blender is feature-rich and contains many different workspaces to perform different 3D tasks, and within those workspaces, they have different modes that refer to different sets of actions. Currently, we are within the Layout workspace, which is commonly used to set the scene and edit meshes. And right now, we are in Object mode within the Layout workspace. Over to the side here, we can see that this area relates to the viewport shading. We can select from different ways to view our meshes, and currently it's set to solid. We can see that it changes once we select wireframe, material preview, and finally back to solid. The drop-down options provide more ways to view the scene, such as being able to view back-face culling. This can be a very important detail to keep in mind for when there's a problem with faces on a mesh that don't appear in our game engine. Near this is a practically hidden arrow which contains Item, Tool, and the View bar. This is where we can view other additional elements, and we can drag it back and hide it just like this. Now that we have a basic understanding of the layout, let's explore some of the modes, starting with Object mode. We select objects by left-clicking them. Shift selects multiple objects. A selects everything. We can remove objects by selecting them and then pressing Delete. Typically, it is a good idea to remove the camera and the light supplied by the template so that we can focus on our model. In this mode, we can also add objects to our scene. Let's add a sphere. We can also see how we may edit some of the properties of the sphere in this dialog box. And just like that, we can remove it. In Object mode, we can also move, rotate, and scale objects. We move by pressing G, or grab. We rotate by pressing R, and we scale by pressing S. Moving the object is nice, but we need to be able to see what we're doing. We can start moving the camera by using middle mouse to rotate, shift middle mouse to pan, and shift grav in order to enter first-person mode. This is really great to use when you're editing a level. There is also an orthogonal camera which flattens 3D objects to a plane. For instance, if we press number pad 1, it flattens everything to the front, number pad 3, right-hand side, and number pad 7, top down. These can be used to more easily modify the object or the mesh. We can see how to use this in conjunction with moving, rotating, and scaling. We can see that I can also move this cube along only the Z-axis by selecting it, pressing G, and then pressing Z. Similarly, I can rotate this only along the Y-axis by pressing R, then Y. We can also snap to the grid, making it easier to align objects. With this active, we can now move with G, then we can press X, which now only makes it move along the X-axis while also snapping to those grid points. Now that we know some of the very most basic object modifications, let's look a little deeper and start editing the meshes themselves. To do this, we first need to select an object and then switch from Object mode to Edit mode. We can do this by the drop-down, or we could do this by tab. Now that we're in Edit mode, we can start modifying the mesh's vertices, edges, and faces. We can do this by using different selection modes found here. With vertex selected, I can move individual vertices. I can even use orthogonal view, axis alignment, and snap to more precisely move them. I can do the same thing with edge selected. For edges, we can also rotate and scale them in addition to moving. And finally, we could do the exact same things with a face. It is useful to select multiple faces, edges, or vertices. To do this, we can use Shift Select. This will select multiples of each one. Control Select selects a path shortest from start to finish. This is useful when we have to define a start and end vertex edge or face. Alt Select selects a loop. This can be very useful for edge selections. We can also press B in order to do a box selection. Anything visible in this box will be selected and everything hidden will not. We can see that it didn't select all the vertices because those were hidden. We can select those by toggling X-ray mode found here. Now we can see through the object. When we box select again, everything is selected. We can now interact with the elements of a mesh, so let's move to more specific kinds of edits for a moment. For face editing, using S to scale would be very useful. We can also extrude this face by using the toolbar or by pressing E. Extruding faces is a great technique for quickly creating simple meshes. For edge editing, it can also be beneficial to use scale. We can add additional edges by using what's called loop cut and slide. You could do this by either going to the toolbar or by pressing Ctrl R. Once we do this, we have to pick an axis and the loop will take place. Then, we slide it along this to make the cut. Once the left mouse confirms it, then it adds an edge. Vertex editing is mostly about repositioning, and they don't have a rotation or a scale. However, we can add vertices by having it in the vertex selection mode and having nothing selected. From there, we can press Ctrl right mouse to add a vertex. We can also make a face from this. If we select these vertices and press F, it creates a face out of it. We can also use symmetry to more quickly create 3D models. Here at the top right, we can see some symmetric modifications that did not appear in object mode. We can see how this works by looking at the face on the left-hand side. If we move it currently, only that face moves. However, if we have X-axis symmetry, then when I move the face on the left, it also moves a corresponding face on the right. These are some of the basic editing tools and features to be aware of. Going back to object mode, we can now also use modifiers to create and edit meshes more quickly. One to be aware of is subdivision of surfaces, which can be used for rounding objects. Now we can see the subdivision of surface has been applied. If we go back to edit mode, we notice that the mesh is still the same, and this remains true until we apply the modification. Now if we go back and apply it, now we see that it did edit the mesh. One thing to keep in mind is we should only apply modifiers once we are sure we do not ever need to modify the underlying mesh. Now we can just simply remove it. Another modifier is called Boolean, which can be used to fuse or cut holes into meshes. Difference can be used to cut a hole. Let's first create a quick cylinder. Now, let's use the difference to cut a hole in this object. We do not see the hole unless we hide the cylinder. However, to ensure that the mesh has been modified, we need to apply the modifier. As we can see when we go into edit mode, the hole is not there. If we forget to do this, then the mesh will remain unchanged. Once this has been applied, we can remove the cylinder, and now we have a hole. We can also use union to fuse together two meshes. We can use intersect to do the same as difference, but in reverse. This lecture has focused on parts found in the application and geometry steps of the graphics pipeline. More specifically, this is only focused on the mesh part of the geometry step. As we can see, there's a lot more to 3D than just the mesh, and future lectures will explore more of these. Now, with all that being said, we are taking this to the next dimension, and I'll see you next time.